my name is Yair Quiroga. I will now present the technical architecture behind our proposed solution for the Gravitar challenge. Basically, our implementation is built on top of a stable baseline tree and uses the Gymnasium library to interface with the Atari environment. As you can see in our file, we chose the DeepQ network, DQN algorithm, because of its proven effectiveness in discrete action spaces like Atari. We basically use a CNN policy to process visual inputs directly from the screen pixels. And now talking about the environment pipeline of our file, we have our function build training environment, in which is basically a key feature of our proposal. This uses a make Atari emp utility to apply the standard Atari pipeline, which includes grayscale conversion and 84 by 84 resizing. This is vital for our setup because it significantly reduces the memory footprint, which was necessary given our current hardware constraints. Crucially, we set the nStack variable to 4 by using backframe stack. Our agent receives the last 4 frames as a single observation. This allows the model to infer motion and direction, which is essential in Gravitar to counteract the gravitational pull of the central zone and the inertia of the chip. As you can see, this is our function. Now, for the part of hyperparameter optimization and sweep strategy, we basically built a JSON file that you can see right here. Basically, we developed a robust sweep methodology. Instead of guessing parameters, we used a JSON-based configuration system, the sweepconfig.json file. Our proposed solution includes 5 distinct experiments. For example, in experiment 4, we balance a learning rate of 1e minus 4 with a buffer size of 100,000 to keep the experience to replay memory fresh without exceeding our RAM capacity. We also implemented a custom TensorBoard callback to log epsilon decay and reward metrics in real time, allowing us to monitor the agent's transition from exploration to exploitation, controlled by the exploration fraction parameter. In summary, our solution combines efficient Atari wrappers with a rigorous hyperparameter sweep to create an agent capable of navigating the complex physics of Gravitar. The architecture is fully modular, allowing us to save and load the best performing models automatically using their own sweep function.
My name is Rosa Alejandra López Lizarazo. In this work, we evaluate different configuration of the DeepQ network algorithm or DQN in the Gravitar-v5 environment with the goal of analyzing how hyperparameters affect learning in a complex setting. Gravitar is a challenging environment where the agent controls a spacecraft with inertia, must avoid gravitational forces, and reach specific targets to obtain rewards. The main difficulty is that rewards are sparse, meaning the agent can act for many steps without receiving feedback. Because of this, learning strongly depends on exploration and on the ability to store and reuse important experiences. We compare 5 different DQN configurations that vary in replay buffer size, learning rate, batch size, and exploration strategy. The baseline experiment serves as a reference. The large buffer configuration aims to improve learning by storing more diverse experiences. The high learning rate experiment tries to accelerate training but may cause instability. The balance configuration seeks a trade-off between stability and performance, and the small batch configuration increases variability through noisier updates. In this graph, we observe the evolution of the average reward during training. The X02 model shows the most stable and consistent performance, mainly due to its larger replay buffer. In contrast, X03 presents strong oscillations, indicating instability caused by a high learning rate. The X05 model also shows higher variability, which is associated with smaller batch size and noisier updates. An important observation is that some agents learn to survive longer, but this does not always lead to higher rewards. Additionally, the results show that agents gradually improve over time, moving from simple survival strategies to more effective behaviors. In conclusion, the best performance was achieved by X02, which combines a large replay buffer, a low learning rate, and extended exploration. Thank you. Excuse my voice, Professor. I have a cold.
Hello, my name is Diego Garzon, and I'm going to explain the best configuration that we use for train the agent. So we do 1 million of iterations, a learning rate low, and an exploration fraction very high, because Gravitar is a game that needs a lot of exploration because there is a lot of planets and variables that we have. So you can see here that the model, for example, learn how to kill that little chip that appears. Also, here in the results of 10 episodes, we have an average of 500 points, and in the episode 3, he get 2000. That is a very big number of points, and it's because he finally can complete this planet. So here in the TensorBoard, we can see that in three in this time of iterations, the difference is not big, and we have someone that goes up and then goes down, so we don't have a really solid results. But when we put 1 million of iterations, here we can see a really big difference, and the model that uh, give us the best results was this one, that has a reward mean of for 4,000. That is very big compared to the others. And also we tried making like a penalizations for the agent if he died, but that makes that the reward was very low, that we can see here in this green line, and this one also. We here the penalization is lower, but makes that the agent gets fear of death, so he didn't get any points at all.